Hello folks, I'll leave back here with a really nice discussion about vectors. This is going to be our second discussion about vectors. We're going to get into the calculus of vectors today. Vectors and Calculus Part 2. Review from yesterday. A vector. A vector is simply a line segment with a specific direction. We're going to change that up a little bit. Well, we're not really going to change it up, but we're going to define this position vector stuff a little bit different here. But the important thing to remember is that it is a line segment with a specific direction. This is a vector, the magnitude that has a magnitude. A vector has a magnitude of a vector. What is the magnitude? It is the length of a segment. And what is the length? A length is what? It is a number. It is a real number. It is a distance. It is a real number that is a positive real number because it represents length. So we're going to talk about magnitude a little bit later, the magnitude of the velocity vector. It's going to be very important for us. And then we have this direction of the vector. We're not really going to be talking about the direction a whole lot about any vectors per se, but we need to remember that the direction is a positive angle from the positive x-axis. So let's start right into our calculus discussion on vectors. Slide number 2 here. And so we have this position vector. A position vector is not going to be a specific segment, but it's going to be a function of t, the position vector. It's going to give us an x-coordinate and a y-coordinate, both of which are functions of t. The velocity vector is going to be, well, time out. The first thing we're going to do is we're not going to make this difficult. This is not a difficult topic in Calculus 2 at all. This is a simpler topic. This is one of the easier topics. So we have our position vector that gives us an x-coordinate and a y-coordinate as a function of t. Sound familiar? And then we have this velocity vector, which is simply just the velocity vector is the derivative of the x component and the derivative of the y component. This is our velocity vector. And we know that the velocity is simply the derivative of the position. A lot of this we're going to reference what we already know about position, velocity, and acceleration in Calculus 1. Motion on a horizontal line, motion on a vertical line. That's where we were a couple months ago. Another way I can denote the velocity vector is v sub 1 of t and v sub 2 of t. This is the first component. This just refers to the first component of the velocity vector. This refers to the second component of the velocity vector. And then I have the acceleration vector, which is the derivative of, and we know the derivative of the velocity is the acceleration. And this is the acceleration vector, the derivative of the first component of the velocity vector and the derivative of the second component of the velocity vector. Okay? Again, pretty straightforward topic. Let's talk about, and I talked about this. Let's review for a moment parametric defined curves, because the position vector is very similar to a parametrically defined curve. And that's exactly what I'm going to start off with as an example of a parametric defined curve, where x is equal to t and y is equal to t squared minus 4t plus 3. And we do remember what a parametric curve is. It's a parametrically defined curve is going to be a curve where the x and y coordinates are given. Both are given as functions of t, as I have here. Now this is a simple one. I've kept this simple for our discussion. They're going to get a little bit more complicated, but hey, we're familiar with this, and we can knock these parametrically defined curves out pretty simple. Well, the position vector is simply equal to, what we're going to do is we're going to look at this parametric curve from t equals 0 to t equals 6. Okay? Oh, well here's the graph of that. At t equals 0, we know that at t equals 0, I have my x coordinate is 0, my y coordinate is going to be 3. And then if I'm looking at this parametric curve from t equals 0 to t equals 6, I actually got this from the graph, and we're going to look at this graph from the graphing calculator here in a bit. But the last point here is 6, 15. I put 6 in. And I know it has a very specific direction. And what I'd like for us to start doing is thinking about this parametric curve as the motion of a bug crawling on the x-axis. I've got this bug crawling on the x-axis. This particular bug started out at time t equals 0 at this point 0,3. And then he started crawling in this direction. And this was each of these points. This is where he is. This is his position. At a particular time, this is his position. Hence the name position vector. What is the vector 615? It is that. That's the vector 615. But let's not think about that. Now, let's just think about, wait, where is this bug at a specific time? I want you to think about just a bug crawling. A bug crawling. The position of that bug. Well, the position of that bug at any time t is from t, is the x coordinate is t, and the y coordinate is t squared minus 4t plus 3. This is the position vector. This is the position of that bug. Both the x and y are functions of t. Very similar to parametrically defined curves. But I want you to think about a position of a buggy. If I think at time t equals 2, this bug is at the point 2, 1. And that point 2, 1 happens to be this point right here. That's the point 2, 1. And I can think about that vector 2, negative 1, 2, negative 1, thank you, as a specific vector. And it is that specific vector. But this is where that bug is, at the point 2, negative 1, when t equals 2. So here's my position vector of my example. T, comma, t squared minus 4t plus 3. Well, the velocity vector is very simple. It's just the derivative of those components. The derivative of the x component and the derivative of the y component. X prime of t, y prime of t, dx dt, dy dt. For our example, this velocity vector is 1, 2t minus 4. Oh, well look at this guy right here. The first component of the velocity vector is 1. This is the first component of the velocity vector. That's v sub 1. V sub 2 is 2t minus 4. But hey, what does this tell us right here? Well, 1's always positive. What does that tell us? Well, it tells us that the bug is always moving to the right. This bug isn't on a horizontal line. This bug is on this curve here. Where's that curve? This bug is on the curve. But if you think about that, that bug is always crawling to the right. Now he's crawling down, but he's still going to the right. He's down to the right, up to the right, down to the right, up to the right. But he is still always moving to the right. The x-coordinates, i.e., are always increasing. The x-coordinates are always increasing. Well, of course they are. The x-coordinates are always increasing. Well, what's happening to the y-coordinates of this motion of this bug? Well, the y start at 3. Well, then they go down to negative 1, so it looks like the y-coordinates decrease, and then at negative. Then at this point here, 2, negative 1, which just happens to happen at t on t equals 2, not coincidence that this 2 and this 2 are just both 2, they don't relate. But what happens now? This bug starts out going down, and then at time t equals 2, he's at the point x2, y negative 1, and then the y start increasing. And look at here. Well, here's the second component. This is y prime of t, or v sub 2 of t, is 2t minus 4. And we know from our previous discussion about position velocity that when the velocity is 0, and the velocity is going to be 0 when t is equal to 2, the velocity which is 2t minus 4, that's going to be 0 when t is equal to 2. I do a little sign chart, and I'm just considering the y coordinate, and I'm only considering from 0 to 6, so from 0 to 2 I put into my test value of 1, that guy's negative. What does that mean? That means that the y coordinate is decreasing, and then if I put my test value over here from 2 to 6, I'm just doing the increasing decreasing test, which we are familiar with. The second component, or y prime of t is positive, that means the velocity starts. That means that the y is increasing. And that's exactly what happened. The y component, the y component of the position, or the bug, the y component of the bug, moves down from t equals 0 to t equals 2. And what I'd like to do at this point, I'd like to show you this, and here's the bug. Now here's this on the, what do I have my graphing calculator set to? I have my graphing calculator set to parametric mode, but what I want to look at here is the table. And if I look at 0, at t equals 0, the bug starts at 0, 3, and then look at the x-coordinates. And I have my t increments in 1/2 seconds, or 1/2 time intervals. And I can see that the x continues to increase. And I can see, hey, what's happening to the y's? They're decreasing, they're decreasing, they're decreasing until -1. That's going to happen at time t equals 2, and then they start to increase. So don't forget about analyzing your graph, the motion of the bug. Don't forget about analyzing the motion of the bug with your graphing calculator too. It helps visualize things. I have this tabular visualization, and I certainly have the graphical representation. Let's go back to my slides here. And let's recall, or let's discuss now the speed of that bug. How fast is that bug going? Well, we talk about velocity, speed, but hey, let's find the speed of that bug, and let's recall what the speed is. The speed of anything is defined as the absolute value of velocity. The speed, absolute value of velocity. We've discussed this previously. Well, if I'm thinking now about a vector, and I'm thinking about position vector, velocity vector, and hey, recall our part 1 discussion about vectors. What does this look like here if I were talking about a vector? Yes, you're correct. It looks like that's how I find the magnitude of a particular vector, and that's exactly what it is. Speed of the bug, the speed of a bug defined parametrically, is going to be the magnitude of the velocity vector at a specific time. I do have this velocity components as functions of time, but if I want to consider the speed, I'm going to look it down at my speedometer. I want to know what my speed is at a particular moment in time. What is the speed? It's going to be the magnitude of the velocity vector at a specific time t. T sub 1, or whatever that arbitrary t value is. Now's when I need to know this discussion that I had yesterday, or recall that discussion about what a vector is and what the magnitude of a vector is. Well, if I want to find the speed at time t equals 3, the first thing I have to do is I have to find that specific velocity vector at time t equals 3. And if I recall, the velocity vector is 1 comma 2t minus 4. If I want to find that specific velocity vector at time t equals 3, I simply put 3 into t. I let t equals 3. When t equals 3, 1 is always going to be 1. At t equals 3, 6 minus 4 is 2. That's the velocity vector at t equals 3. The magnitude of that vector is going to be the speed of that bug at time t equals 3. So the magnitude, the speed of a bug is the magnitude of a specific velocity vector at a specific time. And so if I want to find the speed at 3, I simply find the velocity vector at 3, which is 1 comma 2. The magnitude of that, we know how to find the magnitude. We talked about that yesterday. It's a very easy topic, very easy concept. Is 1 squared plus 2 squared is square root of 5. So square root of 5 then is the speed of that bug at time t equals 3 is square root of 5. Nice. Here's a good discussion. What if I want to know how far did that bug crawl? How far did he crawl? What's the total distance that bug traveled? Not the displacement, not the x displacement. The x displacement was this distance. The y displacement was this distance. We're not talking about displacement. That's a discussion for tomorrow or the next part. I wanted to find the total distance that bug crawled. The total distance that bug crawled. Total distance. Oh, well, let's recall the total distance a bug crawls from t equals a to t equals b. And I recall, this is a formula from last fall. The total distance anything crawls is the integral from a to b of the absolute value of velocity dt. That gives us the total distance, horizontal distance or vertical distance. And we are familiar with this formula. The total distance, a to b, absolute value of velocity dt. Well, what is the absolute value of velocity? What's that? Oh, you mean it's the magnitude of the velocity vector? Kind of. The only difference is we're not talking about a specific velocity vector now, because we're talking about from A to B. But if I were, how do you find the magnitude? It's the square root of the components squared. And so this is the total distance in a parametric curve. The total distance a bug crawls on a parametric curve, the total distance bug crawls on a parametric curve is equal to the integral from a to b of the square root of v sub 1 t squared, of that x prime at t squared, plus y prime at t squared dv. This is the same formula if I had a specific vector to find the magnitude. But look at this a moment. What does that look like? It looks like the total distance of bug. It's the same formula that we use when we're talking about total distance on a parametric curve. The square root, remember, dx dt squared plus dy dt squared. We did this total distance as a function of x, total distance as a function of y. Same formula over and over. But that formula is going to give us the total distance. I'm running out of time here, so I wanted to give this example. In our example, how far, the total distance, did our bug crawl from t equals 0 to t equals 6? Well, recall the velocity vector 1 comma 2t minus 4. So the total distance is going to be then the integral from 0 to 6 of the particular of 1 squared plus that component of velocity squared, which is the square root of 1 squared plus 2t minus 4 squared dt from 0 to 6. That's the total distance. I put this into my calculator, and it looks like it comes out to 21.465 units. That's how far that bug crawled in 6 seconds. If we go back to my graph, and go back to the very original graph here, oh, where is it? Right right here, I think. He's crawled 21. He's crawled 21. Well, look, doesn't that make sense? I could estimate that distance. If I just took that distance and took that distance, that's going to be about, well, it's going to be a little bit more than 21, but it's going to be about 20 or so, because look, this point here is 15, this is 1, and I can see, yeah, 21 makes sense, and that is the total distance. So, what we're not going to do, we're not going to make this difficult. This is a fairly straightforward topic in Calculus 2. So I've got the total distance, our bug crawled formula, which is this guy right here, which is a formula that we've talked about several times before. This is important. I've got the speed of a bug. The speed of a bug parametrically is simply, the thing we need to know is that it is a magnitude of the velocity vector, and it's always going to be a number, a real number. What's the magnitude? The length of a segment, the length of a vector. Length is always going to be positive, so the speed is always going to be, and it's not going to be a function, it's going to be a number. And then we very simply have the discussion of position vector, velocity vector, acceleration vector, and I will let you on your own discuss, hey, what good is the acceleration vector going to be? Plenty. So that's going to conclude calculus, vector calculus, part 2. Thank you.